this webinar is being
Good afternoon, everyone. It is 1 past 2 p.m. here in Toronto, and I have the pleasure of running this webinar on non-destructive testing and evaluation for corrosion in concrete structures. For those of you who don't know me, like my name is Hamed. I'm a co-founder and director structural engineering at F-Prime-C Solutions. I have more than like 20 years of experience in concrete inspection and non-destructive testing, seismic evaluation and retrofit around the globe. And I also sit in some of the committees relevant to concrete and non-destructive testing, both on structures and foundations. So F-Prime-C is a firm specialized in non-destructive evaluation and testing and offers advanced solutions for asset performance management. And as part of this, we thought like maybe it would be best if we dedicate a single topic on corrosion, which is a problem in many industrial facilities. So the agenda for today's presentation is very simple and straightforward. Types of corrosion in concrete. So corrosion is a broad topic. I'm not going to claim that I'm an expert in corrosion. Corrosion in metals can go it's a broad topic. It requires several people from different disciplines to address the challenge. So for the sake of this presentation, I'm going to focus on corrosion in concrete. And unlike many other presentations who just start with complex topics on how the rebar gets corroded, I just want to this presentation being a pictorial guide to make good connections with the asset owners, consultants, and contractors who are involved. So there is tier categories. The good when corrosion hasn't started yet, or at least we don't see anything bad yet, or we are at the design stage and we can prevent many bad things from happening. We are in the control set. Then we have bad, where we have a good structure generally. We are at the early stages of corrosion. We see a little bit of rust here and there, and solutions that we have. And then we have the ugly, which is severely progressed corrosion. We see this in many industrial assets, mainly because concrete structures do not take the top priority in the asset performance management programs. And then hopefully, if I have some extra time, we will dedicate time for question and answers. If not, please feel free to get back to me on my email, hamed@info.fprimec.com, and I'll be happy to work with you on your questions and provide answers where I can. So types of corrosion in concrete. Why and how rebar corrodes in concrete. In general, we know concrete is an alkaline environment. It's good. It can protect reinforcement. So this is a concrete core sample from one of the projects. So it's an actual representation of how corrosion looks like in an actual concrete. So you can see the rebar. Excuse me. You can see the sign of mild corrosion on the rebar, and you can see cracks. So basically, corrosion in concrete has two sections, the anodic reaction and the cathodic reaction, and you can see the chemistry of this reaction here on this. I don't want to get into the details. As I said, there are ChatGPT knows better than me to describe this reaction for you in more detail. So I'm not going to waste time. I'm really here to display applications, use cases of NDT. So I'm going to pass through this very quickly. But in short, there are a couple of agents that can accelerate this corrosion. So depending on how the corrosion has been introduced into your ecosystem, we name them differently. We assess them a little bit differently. So for example, we have chloride-induced corrosion. It's a corrosion that is induced by penetration of chloride ion. Decarbonation, galvanic corrosion, stray current corrosion, and microbial induced corrosion. And now let's dive into and take a look at like how they look. So this is a guardrail in Valparaiso, Chile. So what we have a reinforced concrete element. It is reinforced with regular steel bar. We have plenty of moisture. We have the beautiful Pacific Ocean at the background. And then we have plenty of oxygen as well. And now the second problem that the agent that you don't see here is chloride. So chloride can basically accelerate this reaction. That is why I've called this photo that I took a few years ago reinforced air. So the corrosion has so progressed that you barely see any concrete left. It's a bunch of rebar left there. And the result is that when rust forms on top of rebar, it expands. The expansion exerts force in reinforced concrete, and it induces enough stresses to degrade concrete. If left untreated, it can progress as bad as you can see here. The other form of corrosion is carbonation induced corrosion. So in this one, this is from Middle East, an area that we didn't have any chloride, so we didn't put any chloride in the concrete. There was no chloride in the mixed design, but eventually like carbonation in the area resulted in severe corrosion. And you can see like the carbon dioxide can penetrate into concrete and then make the alkaline environment less alkaline. It becomes more acidic, and it becomes an area environment that is suitable for corrosion and loss of like formation of rust and loss of section. And these are like all real images. You can see like how this entire slab has collapsed as a result of like corrosion. We have microbial corrosion as well. So imagine we are like testing sewer pipelines. It's a very acidic environment. Sulfuric acid is a lot there. Like in wastewater management facilities in general, you can see this type of corrosion frequently. So here we do not really have any chloride in general being the source of corrosion. Here we have sulfuric acid, which doesn't like a cement paste very much. It starts like corroding, like eroding concrete from the surface until like the concrete also becomes like very acidic. The environment becomes very suitable for corrosion reactions, and that is where you can see like the entire cover element has been like degraded and lost. Another type of corrosion is like galvanic corrosion. So this is something that I have frequently seen in many industrial assets. Like people from different trades come and go. Everybody wants to install their own thing. Like one person wants to install this door in this slab. The other guy wants to install like these anchors to support the pipelines. The other one wants to install an additional beam to strengthen the slab. And this is what you get. Eventually everything gets corroded like terribly. Here, like even though like you don't necessarily have like carbon dioxide or like chloride, you can see corrosion has progressed like super crazy. Like this element that you see at the bottom, this is a H beam actually. It is corroded so badly that you could just see like layers of like rust over layers of rust. So when you are placing these similar metals, you are like preparing an environment that is suitable for galvanic corrosion. Now, unfortunately, I didn't have like in my archive here, I didn't have stray current corrosion. So that is like, for example, one good element is like trains that are passing that and powered by electricity. The traverse supporting those elements are very prone to stray corrosion and stray induced corrosion. And the reason for that is not chloride, is not necessarily carbon dioxide. It's the stray current that induces corrosion in those elements. Now, with this quick overview of corrosion, we get into one of the tests that I love very much, and I am very happy to see many DOTs in the States have started picking up that, and I hope to see many of those applications around the globe. So the best thing for corrosion is to not having corrosion at all in the first place. So in order to avoid corrosion in the first place, we have to eliminate those causes, what causes corrosion. So if we have a more durable concrete that doesn't allow chloride or carbon dioxide to penetrate easily, we are basically creating an environment that is less prone to corrosion. If we are, for example, using glass fiber reinforcement instead of like black steel, or if we are using stainless steel rebar, we are eliminating one of the reasons for aggressive corrosion. So these are things that we can control. Now, because this presentation is about concrete, I'm going to focus on how we can test concrete for better durability. One of the tests that is considered non-destructive and can be used in the lab environment and also can be used in the field is surface resistivity of concrete. Now, this was in provisional mode for a few years in AASHTO. Now it is the AASHTO standard, AASHTO T358. It was introduced in 2015. And this is a Venner probe array. So we have 4 probes inducing electric current on the exterior, like exterior electrodes, and then the 2 electrodes in the center are measuring the voltage or like the current. And now by this formula, we are able to calculate the resistivity of concrete. And what it gives us is basically resistivity is an indication of resistance of concrete against the ingress of chloride ion. So it's a matter of like porosity, like it's an indicator of porosity of concrete. So if you have a concrete that is porous, you know this is going to be eventually problematic for you. If it is a concrete that has less pores, so the ions can move in the concrete with more difficulty, it means that it has a better resistance against the movement of ions, and in general, better resistance against corrosion in the future. So previously, people used to do the RCP test, rapid chloride permeability test. So here, in order to put everything into perspective, I am putting this into single table. So actually, TP95 file was the provisional, the same standard, the provisional format. So the numbers hasn't changed. So a chloride penetrability, when it is high, it means that you have like a concrete that is susceptible for corrosion. When chloride ion penetrability is low, which means you have a higher resistance in concrete, then it means that you have basically a higher quality concrete. So these tests can help you at the planning and design stage, set the requirements. So this is a concrete that I want. If previously we used to specify coulombs. For example, many girders in Ontario, then the coulomb value should be 1,000. Now you can go with more strict like guidelines. I need 100 coulomb, which can translate to 200, let's say, kilo centimeter in terms of surface electrical resistivity. And the reason I brought this test is because we can also use this test in the field. And later when we go to the next stage of this corrosion progress, we can review that in more details. Now, the second and stage is the early stage of corrosion. This is not good. It's considered bad, but it is not at the end of the world. We can still live with this, and we can find solutions around this. Now, when an asset owner comes to us for this stage of corrosion, the first thing first is a visual condition survey. So visual condition survey is normally the cheapest and the most cost-effective solution to identify surface anomalies. So an experienced engineer at this stage looks for signs of like excessive cracking, looks for sign of leakage, moisture, rust stains here and there, and puts all this information into one single report and tries to come up with conclusion. Is there any sign of corrosion or not? So this is a good stage. Even when we are kind of asked to only render like NDT, we normally always accompany those with a visual inspection. Now, if you want to take this a little bit forward, like sounding is one of those two. And I put this into NDT because they are NDT. So we are not really damaging anything here. So with this, hammer sounding can basically identify areas that concrete might have become loose, a little bit of like spalling or like, delamination here and there. If you see that hollow sound from concrete, that might be a sign of like early stage corrosion. One of the tests that can be very useful at this stage is half-cell corrosion potential mapping. So with half-cell corrosion potential, one can identify basically if there is an active corrosion happening in the system or not. So the results of the test are categorized in three different segments when you are doing the test with reference to copper sulfate electrode. Now, in this image, you can see, so we have a copper sulfate electrode that is connected to your high impedance voltmeter. The other end of the voltmeter should be connected to a steel reinforcement. So that is one of the downsides of this test, is that you need a connection to steel reinforcement, and your electrode needs a galvanic connection to concrete, which means like we have to make sure the head of this electrode is porous, and the concrete at the connection location should be pre-wetted to make sure that the ions can basically move through concrete. Now, the half-cell potential measurements can vary. So if they are less than minus 350 millivolt compared to copper sulfate electrode, the likelihood of corrosion is generally considered more than 90%. If the values are less and more positive than minus 200 millivolt, then the likelihood of having active corrosion is less than 10%. And the ASTM C876 remains kind of like uncertain for any value between minus 200 and minus 350. So that remains an uncertainty until your next round of inspection. So if you are like doing a test and you see like there are plenty of like yellow areas, always consider repeating the test in few years just to see if things have changed for the good or worse. Now, half-cell corrosion potential mapping is a very sensitive test. It is sensitive to many parameters. So basically, it's not just about knowing how the test works. You have to know the limitations and influencing parameters. So some of the key parameters on half-cell is like temperature. So if you do the test in very low temperatures, which is not generally recommended, you might see different results. If you do it in like freezing temperatures, it's not even recommended. It's not following the standard recommendations. But if you do it in a summer day, the results might be different from when you do it in a fall. Especially in Canada, where seasonal changes in temperature are like really significant. So in your maintenance plan, if you are aiming to test an asset for half-cell corrosion potential, always consider that let's keep it consistent. If you are planning to do it every June, July, let's repeat that every June, July. Okay, so don't postpone your inspection to fall, because then you will be comparing apples to orange, and you don't want to do that with this test. Excuse me. Now, if you remember, when we did half-cell, I talked about likelihood of active corrosion. So I only say if there is a corrosion or there is no corrosion. Like assuming that everything is right and all the settings are correct, this is the maximum thing that I can tell you. Now, one reason that we need other tests to complement this is that it doesn't tell you anything about the kinetics of corrosion at the moment. So it doesn't tell you if corrosion is moving fast or if it is moving slow, like has it already finished the corrosion, or like it has plenty more to go. So here corrosion rate measurement devices come into play. Okay, so now corrosion rate measurement is basically providing an index for how fast corrosion is happening in the structure. So the image that you see, this is an assessment that I supervised. It's a parking garage in Ontario, in Toronto, Ontario. And this was a multi-million-dollar project, and we were in the planning stage, and we wanted to see if these defects that we have identified through like hammer sounding and half cell, are they localized, or they have and like they are moving like super fast. So we should really think about like going with a more serious repair planning, or no, we are dealing with a like kind of moderate type of like corrosion speed, and we still have time. So let's come back in 5 years and do the planning in 5 years. So here is like the typical corrosion rates, and this is a tricky test, to be honest. All those limitations for half cell and influencing parameters also apply to this test. And this test, I'm going to go and say like this test is even more like tricky. You really need to know what you are doing in terms of like how many rebar is under your probe. Like the probe itself normally has a guard ring. You have to have a very good understanding of the amount of like the cross-sectional area of steel that is under your guard ring. And then once you run the test, which normally takes a few minutes to finish, to stabilize and get a meaningful reading with the commercially available devices in the market, this test is generally very slow, like a few minutes for each test point. So we go very selective. We don't like half cell that we go on a very systematic grid. If we want to do that with corrosion rate measurement, this is going to end up a very, very expensive test, and most owners don't wish to do it. But it's a very valuable test in a sense that it provides you with essential information. If how much time you have, are your corrosion moving like crazy? Is it like moving super fast, and should you do something essential right now, or like this is bad, but moving at a very low rate, so I still have time for a very systematic planning. Again, as I said, like influencing parameters here, you have to take into account that concrete ingredients can also like contribute to the variation of like these results. Now, going back to AASHTO test like T358 surface electrical resistivity. So the test that you see here like is the one that you perform on a core sample. So let's say or a companion cylinder in the lab. So let's say you have this sample and you can measure the surface resistivity measurement, and here you can see the value is 246 kilo centimeter. It's a very good value, to be honest. Like if this is for a saturated concrete, this is a very good quality concrete. And to be honest, this is a actual concrete sample from an existing structure in Canada. So we managed to test them before like concrete break test. That is the second advantage. So the same, excuse me, the same core samples that you use for compression test before testing them for compression can be used for surface electrical resistivity. Can you use it in the field? Yes, but terms and conditions apply. So we have used this successfully and unsuccessfully in the field. Okay, we have had cases where we were able to control the influencing parameters very effectively. And this is from a SHRP2 report, like from the TRB. If you can plan this test on a systematic basis, like collecting readings at a regular grid spacing, and then come up with nice little contour maps, and then how you want to interpret this, that's a whole totally different scenario. But you have to take these influencing parameters into account. If you are testing a reinforced concrete with steel rebar, you are going to get like unreasonable results if your probe is placed over the reinforcement, especially if your probe is parallel to reinforcement, and especially if your rebar is close to the surface. Moisture content, for example, you go to a bridge, if you are doing it after like 2 days after a rainy day, or like 30 days in a dry spell in summer, the results are going to be different. So you have to make sure like the temperature and moisture site conditions are kind of like consistent. Now, concrete ingredients tend to affect this test very much. So the same concrete with that particular additive might have a totally different results when it comes to surface electrical resistivity measurement. So take those into account. So now we go to stage 3. This should be section 3 actually, the latest stage, the ugly stage, where things are already like in nasty shape and we want planning. We want to see like what beast we are dealing with. So image on the right is the famous or infamous Gardner column. Hopefully these guys will be fixed like soon. You can see all those spots that have been tested for sounding like loose concrete. The image on the left is an actual concrete slab spalled as a result of severe corrosion in an oil and gas industry in Ontario. Image on the right is a parking garage. So this is an underground parking garage. On top is a pedestrian area near one of those government buildings. It's a government building actually. So the pedestrian area, they put lots of salt to protect the people. In order to protect the people, they didn't protect the concrete. So here we were facing with concrete that was corroded here and there. Bridge structures, very similar. Now with these wide structural systems that we see localized corrosion, the biggest question is, has this cancer of concrete spread to other locations or not? So this is where tests such as half cell become very useful. They can basically guide you how to and where to invest your repair and maintenance dollars on. So this is a problem that is widespread, or this is a localized problem, and if we fix these localized issues, we should be fine. So this stage is basically to assess the extent of defects and to evaluate the severity of the defects. So we want to see how large is the damages and how bad are those damages. So again, in order to see like how much section loss, a handheld caliper is one of the best tools that I have found in my career. I always recommend to people who are in the corrosion inspection, have one of these calipers in your pocket. You don't know, you want to measure thickness, and then you cross-reference it with the existing drawings that you have, and you will be able to get a rebar section loss that is going to be way more accurate than the test on the right. So how fast the rebar is corroding. If you have cross section remaining minus original cross section divided by the original cross section, that basically gives you a better indication of corrosion rate and how fast you have been dealing with corrosion activity in your asset compared to when you are using a non-destructive testing solution for corrosion rate. Works based on linear polarization technique. And I guess I'll get back to this in more details later if we have time. Now, again, when we have large structures, we want to be also very systematic. If we have a long bridge, 2 kilometers, we can't shut down the bridge. We need solutions that move fast. So vehicle mounted GPR are excellent tools for rapid screening of bridge decks. Now, the same thing can happen for parking garage structures. So I call rapid screening because they might not be as accurate as you want. Okay, so they might just provide a global scheme of what is happening in your concrete element, but they are fast. They can move super fast compared to other tests that I will show in the next few slides. So dealing with large areas, GPR scanning, and infrared scanning. These are market standard, in assessment of concrete bridges. They provide very good information, introductory information. So which parts of this concrete slab I need to put my investigation money on and my repair money on. Now that we know problematic zones, we can do more advanced testing such as ultrasonic pulse echo tomography. This basically provides us to refine the margin of defects. So if we have identified this 5 square meter for repair, let's see if the repair needs is really limited to 5 meters, or maybe we can cut down the margins to, let's say, 4 meters. And maybe in 5 square meters, this doesn't end up being a big difference. But imagine you're doing this on a like the 2-kilometer bridge, then this easily becomes a huge problem. So know the problem you're dealing with. This test helps identify potential delamination at the very early stage. So if there is any delamination, this test can basically help us identify those. Another alternative is impact echo or impulse response testing when we are testing thin elements. So as you can see here, we were called to test the concrete wall, and we wanted to see if the same thing that has happened in the right part of the picture, like corrosion, spalled concrete, is basically happening on the left side as well, or like the right side has been like saved. So impact echo basically provides an information about if we have those type of like minor delaminations in concrete. It's a very sensitive test to delamination. It can show us like if we have the problem in shallow depth, and provides very good information. It's a little bit advanced when it comes to interpretation of the test results. So you always need to train a little bit before jumping into interpretation of the test results. Now, the first half of this presentation was talking about the solutions. Now, I want to walk you through some of the case studies, projects that we have been involved in the past few years. And I'll start with some concrete dolphins in an oil and gas terminal. This was a project that our team conducted in Peru. So this is a concrete dolphin. So as you can see, like you can see the onset of like corrosion at the lower part of this dolphin here, sign of like horizontal cracking at the corner, like at the edges here. So these are easily sign of corrosion. Okay, so based on experience, but you also want to make sure like, is this the case or not? So what we did, we developed a comprehensive like assessment plan. We went to the structure. We wanted to not only basically help the client with assessment, but we also like repair and maintenance planning. So we want to see in the corrosion chart, like are we in the initiation phase, in the propagation, and if in the propagation phase, which state are we? Cracking, spalling, how much life is left on this concrete structure. So again, because this is a systematic like project, we start at the very beginning, at the very basic test. So it might be disappointing for you to see like this being this first steps, but these tests basically help us focus over like more advanced technologies in areas that are required. So a little bit of test to identify like quality and integrity of concrete itself. GPR for identifying the location of rebars and the potential like delamination. So we did like GPR on many lines here, like assessment of GPR scans showed like some sign of like GPR anomalies. It's very difficult to characterize like the anomalies here in this graph, like especially in the view that you have here. But here towards the right side, there is a little bit of like sign of early stage delamination, and this part at the center appears to be delamination on top of like steel reinforcement. So we can't prove it right away through like GPR. So we conducted like some half cell potential mapping tests as well to see if we really have like some active corrosion happening here or not. So the results of like half cell confirmed that we have like a little bit of like corrosion near the edges. But generally the top surface was in good condition, and this was in good agreement with the visual condition of the asset. But why did we do this? We wanted to see like those cracks you saw in the first image, they were at the soffit area. We wanted to evaluate from the top because it was easier, it's more cost effective. We wanted to see if the condition at the top is bad, then the condition at the bottom is generally very bad. So that was the like methodology, the overall methodology for this assessment. Then we ran like some, we basically took some core samples from these elements. We tested in laboratory. We identified the chloride at different depths, and we used those information. Like, as you can see, like the chloride content is generally high in this concrete element, which is normal. Like, you are dealing with a structure in an ocean, like Pacific Ocean, and you want to see like how much service life you have. So basically, we go to service life modeling softwares. We enter like the information that we have. We bring all the information from our NDT, and we identify the, okay, so we are right now, we are at like 20 years of your structure. Based on like the information provided, you have like another like few years up to propagation phase, but then after that it's going to go exponentially fast. So you basically have a few years to intervene. Otherwise, you will be dealing with a more costly repair and planning. Now, the case 2 is selected from a concrete silo. And this is an aluminum powder silo in Kitimat, beautiful British Columbia near Alaska. So this is a pre-stressed concrete silo. What happened? Like, the client noticed this beautiful heart-shaped defect on the concrete. It wasn't near the post-tensioning anchorage system, so it was a little bit further, like it was on the shell itself. It was a 40 centimeter thick concrete element, and F'(C) was hired to see if this is a severe damage, or this is a like limited localized damage. So what we did here, we did a systematic grid on or around the defect. We started again, very simple, very basic. So if you are an engineer at your early stage of career, you want to develop into this, you don't need to have the most expensive tools. Okay, it's good to have them, but you don't need to for starting. So you can start cheap with a hammer, with a good eyes to catch anomalies, and then start like step by step. So this beautiful heart was broken out of concrete. We wanted to see what's the reason, if it has expanded beyond this. So we did the GPR as a first stage. We identified a very regular rebar mesh in the shell. And if you are a little bit careful and curious, you can see the second layer of reinforcement here as well. So not so clear, but if we do a little bit of post-processing, we will be able to give it a little bit of a back gain and see those level of rebar as well. Now, we wanted to rule out if this is a concrete problem, concrete quality problem. So we performed ultrasonic pulse velocity and the Schmidt hammer for uniformity assessment to see if the concrete is good quality or not. And as a last stage, in order to see if those like delaminated section is limited to what we visually see, and if the other areas are also affected, we perform the test which we call impact echo. So as I said, like impact echo is very sensitive to layers of delamination. So our analogy for this test was that, like, if this is a solid 400 millimeter concrete thick, the dominant peak frequency should come back at the thickness level. And if we don't see that, and the peak comes at a higher frequency, means that we have a plane of separation at a shallower depth, and that might be delamination. So these are like the impact echo results that we performed on this element. As you can see, beautiful like singular peak in the impact echo, very much associated with the back end reflection. So we were able to identify that we only see these back end reflection with no higher frequencies that might be associated with delamination. So with this test, we moved into the second stages of the test. We hired a contractor to remove the damaged concrete section in order to further study the corrosion. Okay, so we performed like the hammer sounding again on the remaining concrete to see if there is any loose concrete or this has to be removed. We performed half cell corrosion potential mapping in the area to see if we have an active corrosion, or if this is a very localized observation. As you can see, this is a close-up view of the corrosion. One bar at the bottom is generally in a much better condition than the bar at the top. And if you had taken a look at how this area has been like pulled out of the concrete, it was basically like delaminated from this central area. So the top was more exposed to moisture and oxygen. So the top section got more moisture and water, so it's more corroded compared to the bar that is at the bottom. And you can see, like, we performed the half cell corrosion potential mapping. Rebars were in great condition. No sign of like aggressive corrosion in the area was observed based on half cell. So how this information helped like the asset owner? So we were able to identify if there is any structural or durability deficiencies beyond what we also already see. Evaluate the likelihood of active corrosion, which we determined as negligible. Determine if there is any systematic pattern of like anomaly delamination, which we didn't identify through impact echo. And this information helped us like say that the risk associated with this surface defect is generally very low. You can proceed with a minor localized repair. You don't need to go into expensive like repair planning. Now, a case of a conveyor belt. So this is again iron ore export terminal in Quebec. With what we did, basically, the conveyor belt exhibited the sign of corrosion here and there. We wanted to see if this corrosion can potentially become a source of structural concern. So very similar to all other cases, we came up with a very interesting multi-NDT program. This involved half cell corrosion potential mapping, ground penetrating radar, Schmidt hammer, and UPV for uniformity of concrete. And we also performed a perforscope for cover thickness measurement. So one of the issues that we had with this slab was that it's a very thin slab. As you can see in the GPR scanning, you can see that this is a 10 centimeter, like 4 inches thick concrete slab with one layer of reinforcement and more towards the bottom of the slab. Okay. Now, from the bottom side, it had a very small cover thickness, and our understanding was that, like, at the areas that this cover might have been reduced from the minimum specified cover thickness, we are seeing those like sign of corrosion in the area. We performed like half cell corrosion potential mapping at different locations, and interestingly, like the half cell corrosion potential maps from the top and the bottom are different, and that is normal because from the top you are dealing with a much thicker concrete cover, and with half cell there is still no fundamental study on the effect of concrete cover on half cell potential measurement. So these graphs that you see is associated with one of those half cell measurements conducted from the soffit of the slab. Okay, so when you are doing half cell, it's very important to take into account the cover thickness you are dealing with, because that is going to be misleading if you don't take that into account. Now, again, how this information help us help the client. We identified that there is active corrosion happening on a general, systematic basis. So it wasn't limited to one area. It was basically the entire 800 meter length of the conveyor belt. We did like some caliper measurements on the remaining steel bars at the locations, and we specified that there is substantial loss of steel in the elements, and that the structure needs a systematic like repair and upgrade solution, maybe adding like some extra beams to reduce the span of like if you remember here in the GPR, I can't see this, but they were approximately 10 meter span of like concrete. So by breaking that span into a smaller spans, one would be able to minimize the risk associated with that loss of section. The other case that I am going to present, it's a composite deck. It's a Q deck exposed to hot water in a steel factory. It's a corrugated steel, as you can see, and we wanted to evaluate the condition of corrosion. The idea was to help asset owner with repair and upgrade planning with regards to this steel deck, this concrete deck. And we wanted to see if the entire deck has to be replaced or like this is a localized type of repair. Now the idea here, like we know for these type of slabs, those steel beams and the Q deck, the metal deck are the main load bearing system. So we are mainly worried about the steel deck. So what did we do here? We did a little bit of experiment on the concrete. But we also did a very interesting like NDT program and visual inspection program. So we are working like, so this high roof, high ceiling is on casting platform. So hot vapor is spreading all over. Okay, so and it is in operation. So having the idea of like having rope access people visiting this is totally unsafe. So we basically came with the idea if we can eliminate that by using a drone. So we had a drone. We sent our drone in, we got close to the deck, and we identified visually areas that are likely to have corrosion problem. But we also experimented an interesting thing with GPR. So we came up with an idea. So this is the video for the drone, as you can see, like it's a very interesting video. I don't know if you are able to see, but you can see how effective like this drone can fly up to the ceiling. Let's see like how close we can get to the ceiling. And we are talking about like the asset is in operation. So what we are guaranteeing like the owners is like here we are coming with an inspection plan that reduces the downtime of your assets. So as you can see, like we can get as close as this to the element, and then our engineers were on site with our drone specialist, and we came close to every anomaly. We stopped at every turn. We were able to effectively measure this, and the second stage was ground penetrating radar that I was talking about. So what we came with the idea that like we can do a systematic GPR scanning in both directions. And we combined all these like GPR scans into our like software, and what we generated was a heat map of like basically the slice view of like the GPR, and we identified areas that might be anomaly. Okay, so this is still in experimental phase, and then we are still doing some more research on it. But interestingly, like when you put the map of GPR and the map of visual inspection, they kind of match like quite interestingly. So we were able to come up with an idea that if we use a method like GPR, which is like generally very cost effective, especially if you want to do it from the top of the deck, there is a good chance that we can catch some anomalies like corrosion. And the map kind of like cross references pretty nicely with visual observations, and we are like expanding more onto this topic and see like if there is really potential to use this in the future. So we have another example of corrosion in the settling basin, cooling basin tower. Like this project was one of our jobs in Latin America. Again, the area shows plenty of like salt and plenty of water and hot temperature, ideal for corrosion. And as you can expect, like severe corrosion here and there. And the issue we wanted to address, like how can we basically come up with a repair and maintenance plan for this. So again, as you can see, we started cheap hammer sounding to identify all delamination. We performed half cell testing, which was generally all very negative. GPR maps were used systematically to confirm like delamination. So you can see here like steel rebar, and then you can see pattern of like delamination on top of like reinforcement. So very good for catching reinforcement, like coming up with some actual and factual numbers for repair planning. These are the type of delaminations that I was talking about. So you can see like this is a rebar corroded in concrete, and you can see the sign of rust and massive cracking here. And the core hole, you can see spread cracking across the core. And with that, I bring this presentation to an end. I hope like you have enjoyed it. The key takeaway for myself here is that non-destructive testing methods can basically help engineers collect key information about the health and condition of their concrete structure. Depending on how old your structure is, at what stage of corrosion is, and what type of information your consultant is looking for, a multi-NDT program can always help you program more effectively for your maintenance, reduce the cost for repair and maintenance, and also increase and enhance the reliability of your assets. Some of these assets are part of the operation. They cannot sleep. They cannot be turned off permanently, or like even for an extended period of time. So if you can basically, if these type of programs can help you get information on a routine basis about the health and integrity of your structure, it can help you prevent like facing these like severely damaged scenarios in the future. So with that, I'm going to open the floor for your questions and try to see if I can address some of those. Okay, let's see. Slide 16, let me see. Slide 16 is a LiDAR scan. Basically, LiDAR scan, you can do a very quick and fast LiDAR scan using your iPhone or iPad. You can also like go into more expensive like top of the line LiDAR solutions like Leica, for example, or these provide like super accurate solution. So with selecting the tool, you always have to take a look at what type of information you need, and then you customize those testing solutions based on what you need. The other questions here, assuming that all parameters are in great condition, is it possible to assess the remaining service life of the structure after evaluation of the level of corrosion? The answer is yes. So one of the offerings that we have here is like desktop studies. We can always provide desktop studies that basically brings into all these influencing factors into a mathematical simulation and program, and we run different scenarios and we come up with an output that basically helps you have a plan, have a scenario for each case. So you know, like if, for example, chloride is still here, and you have like this concrete with this ingredient, this is how much service life you have in your structure. Can you talk about the corrosion resistivity effect on the design service life 70? How can we increase the design service life by proposing corrosion protection? Is there a difference, reference you can put? So reference, I can definitely provide reference, but the best thing about solution is to consult a corrosion expert. The reason for that is every structure is different. Every exposure condition is different, and each structure is built with different materials. And if you want like 120 years, you have to also provide background information where this structure is located. Okay, so is this in Persian Gulf? Is this in like Gulf of Mexico or Gulf of America, whatever you want to name it? Is this like in a warm region? Is this in a cold region? What is the salinity of the water? And if you have those information, then you can basically come up with scenarios that can effectively postpone and the corrosion. Now, in some cases, you have to implement corrosion monitoring system and corrosion control management plans, like cathodic protection or other type of like corrosion protection systems, like sacrificial anodes. Like those, like depends on like how much budget do you have at your disposal? What is your expectations for like service life? What type of like defects are acceptable from your perspective? So these are things that needs to be taken into account. My good friend Bijan has a question. My question: the standard you use for corrosion rate testing. Okay, so a very tricky question, Bijan. Like there is unfortunately still no standard like for corrosion rate measurement. So as far as I am concerned, corrosion rate measurement does not have a standard. If you really want to go with very accurate results, the best solution is to take like coupons, send those coupons to like labs and perform like linear polarization in the lab or like a mass loss assessment in the lab. And that requires also for you to know how many years this asset has been in service. So you can come up with, okay, this is the loss of section divided by the many years in service, and that is the approximate corrosion rate. Another good friend asking, what is the recommended method to inspect inside the chlorinated water reservoir? There is no access on the opposite side. This is very difficult, Ali, to answer. Like I have many clients asking the same question. So we have done a few like NDT assessment, advanced NDT assessment, where we had access to the top of those walls, but there is only a limited amount of information that we can extract if we don't have access to those walls. So if there is no if there is an access to go inside the tank using a drone, for example, that is one good step to begin with. If that is not possible, then I'm afraid to say like options are going to be very, very limited. And can cathodic protection be used to minimize the corrosion? Of course, it can be used. So for corrosion management system, it's always the balance between the cost and performance goals that an asset owner has. So I go to some facilities and the owner says like, I just want to keep this structure for another 5 years. And sometimes the best solution is just do nothing. Or just provide a safety net or safety mesh underneath in order to mitigate the risk for pedestrian. Sometimes you go to an asset owner who wants to keep the asset for another like 20 years in service, and then that becomes a bigger challenge. Any recommendations for concrete inspection in confined space? Confined space, so far, what we have been able to offer to the market has been basically two solutions: drones, visual inspection, and drone mounted instruments such as like GPR that are controlled by robots. You can crawl them in, collect as much information as possible. I know it's not ideal. You cannot run all the tests that you need. For example, ultrasonic pulse echo. It's a heavy equipment, very difficult. But difficult, unique projects, we always come up with complex, more expensive like solutions. So depending on what your problem is, Usman, we can always see and look into the options. And that is the last question from the first session. So another person is asking me about like the webinar. So I did a mistake. The the webinar, I am presenting 2 webinars today, so both at 2 p.m. or at 3 p.m. So for those of audience who have just joined, don't worry, I will be starting in 1 minute again, all over these presentations from the beginning, so you haven't missed anything. So that was the only way I could avoid like disappointing people. So thank you very much for audience from the last session. If you want to listen to me once again, you're more than welcome. If you are planning to leave, feel free to leave. I am going to repeat this presentation again another time for the audience who are joining me right now. Thank you very much for attending this webinar and hope to see you in our future webinars. Stay with me. I am going to restart this webinar again in 1 minute.